All right, problem number 6. We're going to go ahead, calculate the field from this charge, this distance away. The electric field formula is given by K, Q, over the distance squared. And in this case, that's going to be negative 1.8 times 10 to the negative fourth. That's the Q. Sorry, I got these backwards. Times 9 times 10 to the ninth over 0.03 squared. And when I actually end up working that out, it's going to be a pretty big number. It works out to 1.8 times 10 to the 8th newtons per coulomb. Then we got a 3 times 10 to the negative 6 charge placed in this electric field. We want to know the net force of the charge, so this acceleration has a certain mass. All right. Here we have F is Q times E, where Q is the charge, and that's going to be 3 times 10 to the negative 6th times 1 times 10 to the 5th, and that's going to give us here 3 times 10 to the negative 1 newtons. So now the acceleration, we're going to use F equals ma, and that's going to be 3 times 10 to the negative 1 equals 0.03 times a, and I think that's going to give us an acceleration of 10 meters per second squared. Now, for G period, let's go ahead. We need to do a couple free body diagrams. We'll only need to look at one charge. So we're going to have the tension, and we're going to have the weight, and we're going to have the electric field pushing it back to the left. This angle here is theta. So here we go, and we split up components. We're going to actually end up getting here a t cosine theta component and a t sine theta component. So now let's set up balanced forces in the y direction. That's t sine theta equals mg, and t cosine theta equals qe. The first thing I'm going to do is I'm going to go ahead and I'm going to actually get the angle by doing some trig. I'm going to divide the first by the second equation. So I'm going to end up getting tangent of theta equals, now I'll put in my numbers. So I'll have 3 times 10 divided by my q. Now here, I could say QE. I should have written this a little bit better. In fact, I'm not going to use the QE equation. Instead, I'm going to use the electric force equation, KQ1, Q2 over the distance squared. So let me just go ahead and get that number for the force. That's going to be 9 times 10 to the 9th times 2 times 10 to the negative 6th squared, all over the distance squared, which is 0.05 squared. So I'm going to go ahead and calculate that, and when we do that, this is 3 times 10, and then this denominator, once we get this force, is going to be 14.4 newtons. So I'm getting 30, if I had that right, all right, 30 divided by 14.4 for the tangent of theta. So that means theta is going to end up being the inverse tangent of 30 over 14.4. I'm getting 64 degrees when I do the inverse tangent. And so now I can go ahead and get the tension. I have t times the sine of 64.4 equals 30. And so the tension in the rope is 30 divided by the sine of 64.4. And that's going to give me a 33.3 Newton tension. All right, so that's it for problem number 6.